In the last lecture, we discussed two important problems in linear algebra, and we shall review this since these form a basic foundation for many of the things that we are going to study. The first problem we studied was linear systems of equations. We have an m by n matrix and we are given an m by 1 matrix, and we want to find an x and n by 1 matrix such that A x equal to b. This is the first fundamental problem that we looked at. The first basic question that we raised was, what is the criterion B should satisfy so that the system 1 has a solution. That was the first fundamental question. Once we have the answer to this question, given B, we ask, does B satisfy C? Naturally, for this we may get two different answers, possibilities. We may encounter a situation we get S as the answer, or we may encounter a situation where we get no as the answer. Let us look at what both cases lead to. When it is S, the thing that we can conclude is that solution exists. When we say solution, we mean a solution to the system A x equal to b. So, the moment we are assured that there is a solution, this leads to the following question: how many solutions are there? As we saw last time, this has two possible answers: a unique solution or infinitely many solutions. Now, naturally we ask, when, under what conditions we get a unique solution, and when, under what conditions do we get infinite number of solutions. And when we have the answer to this question, we naturally ask, what is the unique solution? When we are encountering a situation where we have an infinite number of solutions, we would like to know all solutions. We must find all solutions. Now, however, there is a problem of plenty. So, we must have some criterion to choose unique representative. Among the solutions, we must be able to choose a unique representative solution. Now, once we have this criterion, the question we ask is, what is the unique representative solution? Now, let us go back to the other situation where we may encounter no as the solution, the answer to the question, that is, B does not satisfy the criterion for the existence of a solution. Then the conclusion we can make is no solution exists. Then we found last time that under these circumstances we can find what is meant by least square solutions. That is the solution that minimizes the error between B and A x. Then once we have assured that the least square solution exists, we again ask, how many least square solutions are there? How many least square solutions are there? Again we encounter the same situation as before, unique and infinitely many. Again, when is it unique, when is it infinitely many. Then once we have the answer to these questions, we want to find the unique least square solution. And when it is infinitely many and we know when it is, we want find all the least square solutions. Again as before, we want a criterion to choose unique representative, then finally find the representative. So, these are the fundamental questions that arise when we are dealing with a system of equations. Our aim will be to find the answers to all these questions. The other problem that we discussed was basically about diagonalization. The question was, given an m by n matrix P, given an m by n matrix A, find invertible. Now, let us look at a simple situation first. Let us take a square matrix, n by n square matrix, and then phi an invertible matrix P, which is also n by n, such that P inverse A P is a diagonal matrix. We found that this is not always possible, and therefore, we ask the question, what is the criterion A should satisfy so that such a P exists. Let us call this criterion as C. So, we will use the symbol C for the criterion C. Then the given A, we ask, does A satisfy C? As before, we are led to two possible answers, yes and no. Again, when it is yes, we ask find the P such that P inverse A P is diagonal. When it is no, we know there is no such P. So, no such P exists. Now, in this situation, there are two types of analysis we can do. The one is find a P such that P inverse A P is nearly diagonal. Can we do such a thing? And an answer to this would lead us to what is known as the Jordan canonical form. On the other hand, there is another option available for us, is instead of finding one such P, find Q and P such that Q inverse A P is diagonal. We shall see that this leads to an answer to this leads to what is known as the singular value decomposition of the matrix A. Now, the advantage of this singular value decomposition is it allows for generalization to rectangular matrices as well. It allows for generalization to rectangular matrices. So, these are two basic problems which we discussed in the last lecture. Now, we shall look at a third important problem. It must be mentioned that the above two problems are interrelated. You may recall the second problem arose out of reducing the system to a simpler system. Let us now look at another important problem which is as follows. Suppose we start with a vector x, or what we call as a column matrix, and another column matrix, say x is x1, x2, xn, and y is y1, y2, yn, and let us say all are real. So, let us say we have two vectors or two column matrices each having n entries, then we define what is known as the inner product of x and y. We denote it by x comma y with a bracket, and we define it as y transpose x, which is simply summation I equal to 1 to n x I y I. This is a real number. Thus, the inner product of these two is a number. The inner product of two such column matrices is always a number. Let us look at a very simple example. Let us take x equal to 1 0 1 and y equal to minus 1 0 2, then the inner product is simply the sum of the product of the corresponding components, which is minus 1 plus 0 plus 2, which is 1, which is a real number. Now, we do something different. We take another type of product between two vectors, and this is called the tensor product. Let us once again start with a vector x or a column matrix x and another column matrix. Once again, let us take all are real. So, we take two column matrices x1, x2, xn, y1, y2, yn, both of them having exactly n entries. Then we define the tensor product of x with y as we denote it by this symbol x with this into symbol enclosed by a circle, that is the symbol for the tensor product, and we define it to be x y transpose. Now, since x is an n by 1 matrix and y is a n by 1 matrix, y transpose will be a 1 by n matrix. So, the product will be an n by n matrix. So, now previously when we took the inner product of two column matrices was a number. Now, we go higher in the hierarchy. When we take the inner product or the tensor product of two such matrices, we get an m by n matrix. Column matrices now expand and we get an n by n matrix. thus the tensor product gives us a matrix. Now, supposing I can instead of taking an n by n matrix and an n by n matrix, or taking two column vectors of the same size, we take two column vectors of different size. So, that is the generalization we will do. What we do now is we take a column matrix which is x 1, x 2 up to x m, and another column matrix which is y 1, y 2, y n, again all are real. So, one of them has m, the other one has n, and now we define the tensor product of x with y, the tensor product of two such matrices or two such column vectors. We define it to be x y transpose as before. Now, what do we get this time? Again x is m by 1, y is n by 1. So, y transpose is 1 by n. So, the product is therefore an m by n matrix. So, what is our conclusion? What are the entries of this matrix? This is a matrix whose ijth entry is xi yj. So, this is a matrix whose entry in the ith row and the jth column is precisely the product of xi and yj. Thus, the conclusion is the tensor product of an m by 1 matrix X with an n by 1 matrix Y is an m by n matrix. Note, the tensor product of x with y is not necessarily equal to the tensor product of y with x. This is a non-commutative product between matrices and which generates a higher dimensional matrix. Let us look at a simple example. Let us take x to be equal to 1, minus 1, 2 and y to be 2, 3. Then what is the tensor product of x with y? We must take x y transpose, which is 1, minus 1, 2, 2, 3, and when we take the product we get 2, 3, minus 2, 3, 4, 6, which is now a 3 by 2 matrix. Notice that all the rows of the tensor product x y are multiples of y transpose. For example, this row here is the just one multiple of 2, 3. This row here is the minus 1 multiple of 2, 3. This row here is the twice multiple of this 2, 3. So, thus this the tensor product x y has a simple structure. namely all its rows are multiples of just y transpose. So, this is one simple way of generating an m by n matrix. So, taking tensor product x y, where x is m by 1 and y is n by 1, is a simple way of generating an m by n matrix. And the matrix that we have generated has a very simple structure, as we observed. All the rows are just multiples of the row vector y transpose, or the row matrix y transpose. Now, let us push this construction a little further. So, a further generalization, instead of taking one x vector of m by 1 size, a y vector of n by 1 size, let us take a number of them and put them together. So, what do we mean by this? So, consider a positive integer k look at k m by 1 matrices or column vectors u1, u2, uk and k n by 1 matrices v1, v2, vk. Now, we will form the tensor product of u1 with v1, u2 with v2, uk with vk. So, for each I, 1 less than or equal to I less than or equal to k, look at the tensor product of xi with yi. Now, since xi is m by 1, yi is n by 1, the tensor product will be an m by n matrix. This will be an m by n matrix. Now, for I equal to 1 we get one m by n matrix, for I equal to 2 we get one m by n matrix, and so on. Finally, for I equal to k we get one m by n matrix. If we add all this, we still get an m by n matrix. I am sorry, this should be ui tensor product. Okay, so now for each I we get a m by n matrix denoted by this tensor product. Now, let us add all this. We get summation I equal to 1 to k ui tensor product with vi. Since each term is an m by n matrix, this is an m by n matrix. Right. Okay. So, now we see that we are able to generate m by n matrices by such sums of products. We can generate lots of m by n matrices by varying the number k, that is whether you like to add k such tensor products, one such tensor product, 2, 3, 4 and so on. So, you can choose the number of tensor products that you use, that can be changed, and we can change the u1, u2, uk, we can vary the v1, v2, vk. So, we have lots of options of changing these combinations, and each time we may end up generating more and more different m by n matrices. So, we can generate a lot of m by n matrices by this process of tensor product sum. The fundamental question is, does this construction exhaust all m by n matrices? Does this construction exhaust all m by n matrices? What does this mean? This means given any m by n matrix A, can we find 1 a positive integer k, 2 column matrices u1, u2, uk m by 1 matrices, that is m by 1 column matrices, v1, v2, vk n by 1 column matrices, such that A can be now expressed as the sum of all these tensor products ui, tensor product pi. This is the question. Now, if we can do it, we can see that A has been split into a number of small simple matrices, because each one of these tensor products has a simple structure, namely every row is a multiple of a fixed row, namely the ith row is a multiple of Vi transpose, and therefore, that would break the matrix into simpler parts. The answer we will see that the answer is S. This leads to the following question. Now that we are assured that a matrix A, an m by n matrix A can be broken into such small pieces, each one of which is simple, we would like to do it efficiently. So, what is an efficient way of doing this? That is, what is an efficient way of expressing a given matrix A as the sum of tensor products? Now, first of all, we would like to have as few terms as possible. So, that is, the first question is, what is the minimum value of k required, that is, what is the minimum number of sums that you have to take in order to construct the matrix A. Of course, the answer will depend on what is the matrix, the properties of that matrix. So, what is this number k will depend on A. The second question is, having fixed that number k, say minimum is rho. Usually, eventually you will see that rho is the rank of the matrix. Now, having fixed that minimum number, can we choose u1, u2, u rho, these are the m by 1 matrices, v1, v2, v rho, the n by 1 matrices that will appear in the tensor product, such that the matrix A equal to I equal to 1 to k ui vi is now easy to analyze. What do we mean by easy to analyze? For example, can solve A x equal to b using this decomposition, expressing A as the sum of these tensor products, we can solve A equal to b easily. Now, an answer to this question will again leads to what is known as the singular value decomposition. We have already seen a singular value decomposition earlier. There we were trying to express the matrix as the product of matrices. Here we are trying to express the matrix A as the sum of matrices. Both have closely related to each other. We will when we get to these details, we will see all these are totally related to each other. This is another important problem. In particular, the way we choose the ui's and the bi's would make not only solving the system A x equal to b easy to solve, it would even help us in compressing the data that the A stores. Before we begin our formal study of linear algebra, we would look at one more important problem connected with matrices, or one more important problem of linear algebra. This we will call as the fourth problem. This is again connected directly to the systems of equations, and we will later will find its connection with the singular value decomposition, etc. Let us recall that when we have a system A x equal to b, we had situations like, does B satisfy the condition C for existence of a solution. We had two situations, yes and no, and the yes led to two situations, the unique solution and the unique representative solution. That is, in the case when there are infinite number of solutions, we had to pick one of them by using some criterion, so that our final answer is a vector x. In the case of no, we had least square solutions, and this again gave us two situations, unique least square solution, the unique least square solution, and the unique representative least square solution. Now, we see that finally, in all the situation we are looking at the unique solution, in this case, in the first case, the unique representative solution, the unique least square solution, the unique representative least square solution. Therefore, in all this finally we want the answer to be one unique vector. So, we have this situation. The situation is, we are given B, we want to find in each one of these cases the solution. When we say the solution, we mean the unique solution in the first case, the unique representative solution in the second case, the unique least square solution in the third case, and the unique representative least square solution in the fourth case. We will in general denote this by x naught b, because it will depend on b and it is a vector or a solution matrix, m by 1 matrix, n by 1 matrix, and we will denote it by x naught b. So, our answer is finally to find x naught b. This x naught b, again I repeat, will represent the unique solution whenever the unique solution exists, the unique representative solution whenever there are an infinite number of solutions, the unique least square solution when the least square solution exists only and unique, or the unique representative least square solution when there are an infinite number of least square solution and we pick the unique representative. So, our final job is we are given the vector B, produce me the vector x naught b, which is the ultimate answer to your question about solving the system of equation. We can view this problem in the following way, namely, let us look at the matrix as the transfer matrix or the transfer function of a linear system. What does it do? When we have an input x, which is an m by 1 vector. So, the permissible inputs for the systems are all m by 1 matrices. When we input an m by 1 matrix, the output is going to be Ax, which is an, so if we put input n by 1, the output is going to be m by 1. What we are asking is, when we solve Ax equal to b, means we are asking for a particular output b and we would like to know what the input x is. So, we are looking for the input x which will produce the output b. Our answer should be that x naught b. What do you mean by x naught b? Whenever there is only one input that produces the desired output b, x naught b will be that. Whenever there are several inputs which produce the same output b, then the x naught b will be the representative input which produces b. Whenever there is no input x which produces the output b, then we will be looking for inputs which will take you as close to the required output b, that is, that minimizes the error. So, whenever there is a unique minimizer or the unique least square solution, that input will be the x naught b. Whenever there are several inputs which give the same minimal error, then x naught b will be the unique representative input. So, x naught b is our final answer. If you want the output b, x naught b is the best that can produce it. It can probably go to b and nobody else can give better answer than that. That is what the final answer should be. So, we are given b, from that we are trying to construct the x naught b. So, we are given the required output b, we would like to construct the required input x naught b. So, in other words, we are trying to control the output b. So, therefore, what we would like is, we are only given b, we have to do some calculations on this b to produce the x naught b. So, this boils down to, we are constructing another system for which it has another transfer function, we do not know what it is, we will denote it by a dagger, for which we are going to put the input b and there is going to be an output because of this, which is a dagger b. We want to construct a dagger such that this a dagger b is our ultimate answer to our linear system. Naturally, we are expecting x naught b to be n by 1, b is m by 1. So, therefore, a dagger has to be constructed as an n by m matrix. So, the fundamental problem therefore, is the construction about the system of equations is the construction of this matrix A dagger. So, main problem is given an m by n matrix A construct an n by m matrix A dagger such that x naught b is equal to A dagger b. I repeat again, x naught b has different connotations on different situations. When there is a unique solution for A x equal to b, x naught b represents the unique solution. When there are infinite number of solutions for A x equal to b, x naught b represents the unique representative solution. When there are no solutions for A x equal to b, and if there is only a unique least square solution, x naught b represents the unique least square solution, and when there is only least square solutions, but infinite number of them, then x naught b represents the unique representative least square solution. So, the fundamental problem therefore is in the systems is given the matrix A, which is m by n, construct the matrix A dagger which is n by m such that x naught b is equal to A dagger b. So, the moment you play your b, I will send it through A dagger and produce my answer x naught b, which is the best answer possible for the system A x equal to b. This A dagger, this leads us to several things. One, inverse of A whenever A is a square matrix and as an inverse. And in the general case, whether it is an inverse, whether it is square, whether it is rectangle, etc., it is called the pseudo inverse. Of course, the pseudo inverse will be the same as the inverse whenever it makes sense. So, this leads us to the notion of the pseudo inverse of a matrix. Thus, we have looked at 4 problems. 1, the system A x equal to b, the 4 problems we have studied or we have just generally discussed, which are going to form the backbone of the various studies that we are going to do in linear algebra. Then we looked at the question of diagonalization and near diagonalization. Then we looked at the question of decomposition of a matrix as sum of tensor products and finally, the notion of the pseudo inverse. Now, we should not lose sight of the fact that the second, third and fourth problems are consequences of the questions that we asked in the first problem for the linear systems of equations. So, they are all highly interrelated problems and go hand in hand, one helping the other or one leading to the other. In the therefore, in answering 2, 3 and 4, the major role or the decisive role in 2, 3 and 4 will be played by the notion of eigenvalues and eigenvectors. If you look at the problem 3, in which we are decomposing a matrix as sum of tensor products, two important situations in these are the following: one, when A is a square real symmetric matrix, two, A is what is known as, we will look at later the definition, a square normal matrix. In the case of complex, we should look at Hermitian complex matrix. This decomposition is what is known as the spectral decomposition for these matrices. As observed above, the eigenvalues and eigenvectors play a crucial role in all this analysis. Our goal for the course shall be the following: one, develop the mathematical framework for analyzing these problems. Two, find the answers to the various questions raised in the above problems. Three, look for generalizations and abstractions of these ideas. The main discussions in the course will be driven by these three goals. All our attention will always be to eventually to attain these three goals. We are now ready to begin a formal course on linear algebra. What we have seen is only an overview of the important problems that lead us to the study of all these aspects of linear algebra that we shall be covering in this course. So, before we begin our course, we shall give some standard notations that we will be using in this course. So, the first thing that we will study will be the linear systems. The notations that we will use are the following. Most of the time we shall be dealing with matrices whose entries are real or complex numbers. So, what we will do is we will use the general notation F, which may denote the real numbers R or the complex number C. R denotes the set of all real numbers, C denotes the set of all complex numbers. Whenever necessary, we will mention very specifically whether we mean R or C. If we do not mention, then it could be it would work with f as r, it would also work with f as c. Then by f k, where k is any positive integer, we shall denote all column matrices with k entries, that is k by 1 column matrices, where all these entries are from f. So, when we say R k, we mean all the entries are real numbers. When we say C k, we say all the entries could be complex numbers. In particular, by theta k, we will denote the vector or the matrix k by 1 matrix whose entries are all 0. Then by f by m by n, we shall denote all matrices which are m by n matrices and all the entries are from f. And in particular, by 0 m by n, we mean the 0 m by n matrix, that is the m by n matrix, all of whose entries are 0. And in particular, when m equal to n, we get f n squared, the set of all n by n matrices such that a I j is from f. And in this situation, we shall denote by I n the n by n identity matrix, 0 n to be the n by n 0 matrix. With these notations, we shall begin in our next lecture the study of linear systems of equations.